Hey, this is the Unretired engineer coming at you again with another story from my history in the defense and EV industry. Today I'm going to be talking about onboard vehicle power, OBVP, and the transmission integral generator. The transmission integral generator is a key enabler of the future battlefield and future deployable power, but it's a technology which did not come from a government spec. It was developed by a team of people in industry who understood the need and had the technology for the solution, but were actually constrained by the specs that the government kept on giving out. We'll talk a little bit about that and other things. What led to the breakthrough was the teaming of technical people from multiple business units within DRS and with Allison military vehicle integration team, understanding what the need was and then developing the maximum possible solution that was reasonable within the industrial capability of the platforms. What we achieved in the end was a massive increase. I mean, most vehicles today, there are a few kilowatts of power. A lot of power generated by a belt-fed generator is 12 kilowatts. Above that, your problem rapidly becomes the belts break and the bearings fail and all the rest of that. Most other solutions where you put a pancake machine between the engine and the transmission makes the drivetrain longer, and it makes a lot of complexity in upgrades and retrofits and whatnot, which is just not viable in many cases because military vehicles are usually very constrained in space. This solution will provide 30 kilowatts of power while you're driving down the road. But when you park the vehicle and run it in a stationary gen mode, it can provide up to 125 kilowatts. And that can power a laser, it can power radar, it can power a HQ, or it can power a mini mall or a subdivision in a disaster. So it has many applications in the military and civilian defense field. To bring this to the field, it basically meant we had to break the standard paradigm of the military gives you a spec and you develop it. That wasn't working. And so we moved beyond that to bring the solution. In the 90s and the early aughts, the solution for mobile power in the field was to tow a generator, right? And one Humvee could tow a 15 kilowatt generator, so 30 kilowatts, which was really what the minimum requirement was, required two Humvees to tow it, or it required a medium truck to tow a 30 kilowatt generator. And then that generator got to a site, it was parked, and then ran. And essentially, most generators, they're not super efficient and they require maintenance of their own, etc. And so the logistics for that is pretty extensive. Back in the prior century, right, the predecessor to the DRS team had built a solution using one of their permanent magnet machines, and they had developed in-house a power converter that took the power from that machine and would output 230, 120, or 230 multi-phase, whatever you needed in that range. But what it was essentially they would take the Humvee transmission, they would cut the bell housing off, they take the torque converter off, they would mount the machine to the torque converter, and then they had a whole standard. This provided 30 kilowatts of stationary power and a significant amount of mobile power without really affecting the overall drive line length by much. But it did affect it, and there was a big logistics issue of the change in the machine, in the torque transmission, etc., all of that. It meant there was a big logistics issue about how did you support that in the field. And the Army, who controlled that vehicle, were basically not that thrilled with that solution. And of course, by then, the Humvee was becoming a bit obsolescent, even though then it went on in the Iraq War to be one of the primary vehicles and was up armored, up engined. And they continued to want 30 kilowatts of power. But most of the time, what they would do is they would put a big alternator on the front of the engine. Problem with that is once you get to 20 kilowatts or so, really much above 12 kilowatts, you kill the engine because the front bearings and all the rest of it, and then your rubber belts or whatever belt you use, it all wears out very, very quickly, and it's really not a solution. But that was the road that they went. The OBVP had been funded by the Marines, and they actually got money so that a small number of units, about 20, were actually deployed. Marines loved them. You saw demos of them hitting the beach and these vehicles rolling off and rolling up, and then the follow-on ones with the tow-behind trailers getting stuck on the beach. And there was one episode where the 24 hours before they were able to get the tow behinds pulled up, but the HQ had been running all of that time on OBVP. The Army said, well, that's the Marines and we're not that interested. And so it kind of went by the wayside. You come to the war in Iraq, Afghanistan, all of that. And you have MRAPs and you have Strykers and you have and the need for 30 kilowatts and then now 70 kilowatts comes up. And again, they still try and do bolt-ons. There were programs where they strip the whole front of the engine off and rebuild it with one generator. None of it worked. There were a series of programs where you put pancakes in between the torque converter and the generator, and that wasn't very successful. It added a lot of cost, very non-standard, and it didn't fit very well in a lot of the vehicles because the vehicles were designed around be as short as possible. So they used the engine and transmission length was what drove the length of the vehicle. So adding length to that just didn't work very well. Again, none of that really worked. And so DRS saw that. There wasn't really, a lot of joy in our land. We did work on the converters, but the machines and whatnot, we worked on a number of things, but they weren't really. So we had started to work with the premier transmission company within the United States, Allison Transmission. Their 3,000 and 4,000 transmissions, which go in commercial trucks, so the same transmissions that go in most wheeled military vehicles, same transmission. They also build the transmission for the M1 tank. Abrams tank. Through the 90s and the aughts, they had answered a whole bunch of RFQs and hadn't really gotten anywhere because the Army wanted radical changes to the transmission, and Allison said, we can't do that. We can't do it affordably. Can you do something else? And the Army just basically kept on batting it back. So about the time that I joined DRS, one of the things I did, because I came from Indiana and had a little knowledge of the Allison transmission, I started talking to Allison Transmission. We worked on a number of different things, one for the Abrams tank, because it had the same desire for 30 to 70 kilowatts. We also looked at Stryker and MRAPs and all the rest of it and what you could do with the 3,000 and the 4,000 transmission. But the problem is we were responding to RFQs, to the spec from the Army, and those specs simply asked for things which were not feasible. And when we didn't answer those things, they gave the project again and again, they gave it to somebody else. The problem with that is every one of those programs collapsed because they overpromised. They couldn't do it within the cost margins. It was just a mess. And so I and people from DRS, from the power group, and Allison, we went to conferences together. We talked to customers together, and we basically developed the idea that there really had to be a different way. So the first thing we did, the most used transmission is the 3000 transmission. We said, okay, that's the wheeled transmission. What can we do? And the solution was power takeoff. Right? We turned mechanical power takeoff to electrical power takeoff, and I coined the term TIG kind of almost offhandedly, and eventually that became the program name and transmission integral generator. And the integral was the key thing, because we basically said you can't make it any longer. It has to fit within the length of the vehicle as it exists today. It can't change anything very much about the transmission at all. The bell housing was about the only thing, and then some bolt-up things we discussed, and even those things at the end we didn't change, other than I think we have 7 or 8 custom bolts for part of the bolt-up. But other than that, the bolt-up is the same, and then it has a custom bell housing and the custom machine, which is integrated. So this is a model of the 3TIG or Allison transmission with the transmission integral generator integrated, showing basically that it is the standard power takeoff version length and diameter. So this model was created by the Allison team. It's one of several that we used as a marketing tool, going to customer meetings and going to conferences to explain the theory and what we were developing. So we went to a bunch of different companies, people who were building vehicles, as well as people who needed the solution. Didn't get us a lot of development money, but it did give us quite a bit of partnerships, because people were very interested by the technique and technology. So this model is a bit cool. It was built in the aughts tens. It's a cornstarch type material that was in a powder bed, and then they jetted an adhesive and the colorant onto it to create this 3D, very cool, pretty accurate model that was easy to handle. It does not functional in any way, but for a 3D cutaway like this, it's really useful. Came in very handy a lot of times. So, what this really shows is that we take a very standard 3000 transmission. This is the standard gear body. This is the standard torque converter. And what is modified is there's a new bell housing, which Allison designed around the machine. And then DRS designed the rotor, the machine, and then the bolt-up, which is the standard bolt-up. So the bolt-up for this is all standard to the 3000, no changes to the 3000. That was one of the key elements. So the rotor is here. You can see that there are a few bolts here in the torque converter assembly, which are a little bit longer than standard. So to take the torque, to take the rotor. And that was pretty much it as far as that was concerned. So this is the rotor, and it was one of the things we had to develop. Obviously, we were working within this very tight environment to make sure that the machine took up as much of the volume as possible, but not too much. And then we had to make sure the rotor was attached to the torque converter in a way that was safe and reliable. And so that was actually finding an iron, a steel, that was a good magnetic material for the back field of the magnets, was also strong enough, and we could machine into this fairly complex shape. That was one of the technical hurdles we had to deal with. So then you can see the stator. These are the windings. This is the back iron, and then this is the water ethylene glycol channel, which was basically the piece that also attached the machine to the gear body, and again, standard bolt up here. So then the housing is as standard as possible, but it does have this interface for the water coolant jacket, so the inlet outlet. And then this side is where the stator terminates and comes out to the outside. So, essentially, as long as your vehicle can take a power takeoff Allison transmission, this is the 3000, but the 4000, as long as it can take that, it will take this machine. Building the machine into the transmission meant that there were things we sub-optimized from an electric machine viewpoint. We would have maybe liked a little bit more volume or whatever, but we had to fit it within very narrow constraints. Had to bolt it up to the torque converter, not try and connect it down to the splines on the main shaft, because that basically meant that we had to cut the length of the machine by several millimeters or a couple of centimeters. And it just didn't work. That you couldn't get the power. So we defined that what is the maximum feasible power, and we basically use that as our target. That's what we're going to do. And then the rest of it was, it has to fit within the existing PTO, and it has to be easy to build and essentially supportable by anybody who can support a Allison transmission, and we succeeded in doing that. We built multiple kits of the power electronics as well as the machine. Allison made all the custom pieces and integrated the machine into the transmission. We went to a number of different companies and got agreements with them. We actually built those units into MRAPs on program money, and took it to the network integration field exercises that were being run through I think they ran from 2011 to 2018 or so, of field exercises where they brought all the electronic stuff and played around with it while they were also doing war games. And again, the MRAP power generation systems we showed, it really got the senior officers really worked up, because it solved so many problems. A lot of them basically went away swearing that they wanted to take it back to their next deployment. The general who went to Korea said, I want 10 of these to go to Korea with me. That didn't happen immediately. Things take longer when you're talking about this sort of thing. There had to be some changes, I think, within the DoD to accept this more industrial solution. But today, we're actually making good progress. The Army has awarded DRS the contract for the kits, for multiple of these as vehicle backfit kits. So exactly what we said. They can now put them on Strykers. They can put them, and they've done the engineering to integrate them on Strykers for laser weapon systems. They've done it, for radar and for headquarters. They've done it with, again, still with MRAPs. They're working on JLTV. They've working on the 4000 with an application for one of the larger vehicles. So they made real progress, made a breakthrough. It is actually going out there and being fielded. So the system develops 120 up to 125 kilowatts of power stationary, and up to 55 kilowatts today when it's on the road. So you can have a huge amount of power. I mean, even drive a laser, maybe not at the rep rate you can do stationary, but you could probably do it on the road. Because the other thing that's kind of interesting is, even when the engine is idling, right, you can pull off about 10 kilowatts of power even when the engine is idling. You don't even notice the fuel change in the fuel burn, because there's just a certain amount of energy going out there, and most of that energy is going out the tailpipe as heat when you're idling. But when you have the TIG on there, the TIG is pulling the power out and turning it into electricity. It doesn't affect the fuel efficiency, which is really interesting. The other thing is because it's integral to the drivetrain, there's no additional maintenance other than what you do on the transmission anyway. It's much more effective. The uptime for the generators is much higher than you do on gensets, which have a tendency that they're inherently pretty reliable. The problem is they don't get great maintenance, and they just sit there and burn fuel and generate electricity and get ignored until they break. Whereas on a vehicle, they tend to get better maintenance. I think one of the key takeaways is specs react to the last war. The other is that what the customer needs and what the customer want are sometimes somewhat divergent. And when they're willing to pay for what they want, that's one thing. But when they demonstrate again and again and again that they can't pay for what they want, but they still have a need that they're willing to pay for, that sometimes you need to step in and build a team who can take it and move out with a spec that is achievable, within the funding, internal funding of the team, to do a demonstration, to get it to a point where you can show, yes, this is a viable product. It's more than a minimum viable product, but it maybe doesn't have all the exquisite details you wanted, but it still fits the need and solves the problem you really have. And that's what the 3TIG does. So I think, we didn't build a new generator. We ended up basically changing the face of mobile warfare and moving it to the next stage. I think that it's pretty easy to say that. It was a cool program, and one that I regret having to leave before it came to fruition. But the people I worked with, a lot of them continued, though sometimes they shuffled around company a bit. But they're still out there working on it, doing great work, and bringing this to the warfighter at a time of need. So that's great. I'm the Unretired Engineer. If you like this, again, please hit the like, hit the subscribe. If you have a question or a comment, please hit the comments line and send me a message. I will answer it as soon as I can. Channel update. I'm still working on my sci-fi novels to update and then bring out new ones as well. And learning what I can about AI as a tool and how to use it to enhance human capability, not to try and replace it. There's a lot of cool stuff out there, a lot of cool technology to play with, and we all need to keep on keeping on and just push forward. I think there's always maybe old doors close, but new ones open up, and those prospects can be much better than the ones you thought were there when you were kind of just doing the daily grind. So that's it from the Unretired Engineer, signing off. Cheers.